Hey everyone, and welcome to this tutorial. Today we'll be using PyTorch to create sequence models using long short-term memory networks, that is LSTMs, as we discussed in the last tutorial. So up to this point we have seen feed-forward networks before LSTMs, and those feed-forward networks did not have any maintained state in the network at all. So in case of NLP, we want a state to be maintained, a hidden state. And sequence models are central to NLP. That is, they are the models where there is some sort of dependence through time between your inputs. And the classical example of a sequence model is the model for part of speech tagging, which is what we are going to build in this tutorial. In case of the LSTM, for each element in the sequence, there is a corresponding hidden state, that is h of t, which in principle can contain information from arbitrary points earlier in the sequence. One thing to note is that PyTorch's LSTMs expect all of its inputs to be 3D tensors. So let's move on. Let's begin by executing all of these. This is the standard import functions that we see, and this line of code basically ensures that you'll be able to reproduce all of my results, so you can follow along with executing this side by side in your Google Colab notebook. So the model that we have is that we have an LSTM to get part of speech tags, and we'll have an input sentence that will be composed of m words, that is w1, w2 up to wm, which are the words, and all of those words will be belonging to our vocabulary of terms. And then we have a tag set, that is t, and yi will be the tag of word wi, and the tag is essentially the part of speech that that word corresponds to. And the prediction of the tag for the word wi will be yi hat, that is the predicted value of yi. And this is a structure prediction model where our input is a sequence yi hat up to ym hat, where yi hat belongs to t, the tag, the list of tags. So for the prediction, we pass over an LSTM over the sequence. We denote the hidden state as hi, and we assign each tag a unique index. We take the log softmax of the affine map of the hidden state, and the predicted tag is the tag that has the maximum value in this particular vector that is generated as a result of this operation. We use this code to prepare the data for our model. So the training data over here has these two sentences, say. So this is the first sentence, and we split that into its individual words. And then this is the list of tags that we have, that is the ground truth values. This is the correct predictions for all of these words in this sentence. Det stands for articles and prepositions, and NN stands for nouns and pronouns, and V is a verb. So 8 is a verb, and dog is a noun, and so on for this sentence as well. Then there's this dictionary, word to ix, that's a blank one right now. And for send tags in training data, that is send is all of these words and tags is all of these tags. For every word, if the word is not in this dictionary, we add that word to the dictionary, and then we assign the corresponding number based on the length of the dictionary, that is a sequential order from 0 to whatever number of words are there, and then we print that. So the corresponding numerical representations for all of these tags are 0, 1 and 2 respectively for these. The number of embedding dimensions is 6, that is when you convert each word to its word embedding, the dimension of that vector, that is the embedding, will be 6, and hidden dimensions equal to 6. And this prepare sequence function converts each word in a sequence to its corresponding indexes. Next, let's create the model. The class that we have is LSTM tagger, and the init function has all of these important parameters. So we define the super for this, and then the hidden dimension for this is the hidden dimension specified here. The word embeddings are with the use of the function nn.embedding, which takes in vocab size, that is the size of the vocabulary, that is the total number of words in our vocabulary, and the number of dimensions in the word embedding. The next thing we have is self.lstm, which is nn.lstm, that is the function used, and this takes in the embedding dimensions and the hidden dimensions. Hidden to tag is essentially the linear layer that maps from the hidden state space to the tag space. So this is a linear network, that the first kind of network we saw the most simple one, and this takes in these dimensions. And then the hidden layer, we also have init hidden, where the matrix is defined as a matrix of zeros based on the hidden dimension. Next we define the forward function for this, which has the embeddings as word embeddings for the given sentence that we put in for this function, and lstm out and hidden is equal to self.lstm with the embeddings converted into this format 3D tensor, and then self.hidden is passed in as well. The tag space is created with the function that we defined for hidden to tag, and then the tag scores are calculated with the function that I mentioned in the beginning, that is the log softmax of the tag space. So this will eventually give us the prediction for our part of speech that the word corresponds to, and then we return these tag scores from this function. Next we move on to training the model, and the model is defined as LSTM tagger, and all of these parameters are passed in it. And then we define the logs function, which calculates how accurate our predictions are. The optimizer is defined as the stochastic gradient descent optimizer, which is the SGD optimizer. So all of the gradients in the function are defined to 0 here, and then we get the inputs as the prepare sequence function that we defined in the beginning over here, that converts every word to its index, and then we put in all of these parameters in there. We get the tag scores from the model where we pass in these inputs, which is got from here, return tag scores. And then for 50 epochs, that is for 50 passes through the network. So step 1 over here is that we should remember that PyTorch accumulates gradients and we need to clear them out before each instance. So this initializes the gradients to 0. Step 2 is that we get our inputs ready for the network, that is we turn them into tensors of word indices, and this is done with this sentence in prepare sequence, and we define the targets as preparing the targets. Step 3 involves running our forward propagation, that is the forward pass through the network. We pass in the sentence in through the model and we get the corresponding tag scores for each word of the sentence that is passed in. Step 4 involves having to calculate the loss and the gradients and updation of parameters. So the loss is the deviation from the actual ground truth value that occurs between our parameters and the actual ground truth values. And then we calculate the gradients using the loss.backward function. This is backward propagation through the network. And then optimizer.step ensures that the weights and the bias terms are updated using these gradients calculated from this, which leads to a better prediction in the next run. So next we see, in this case over here, we see what the scores are after training, and the sentence the dog ate the apple, I, j corresponds to the score for tag j. For word I, the predicted tag is the maximum scoring tag. So based on the values of these numbers at each of these rows, we get the prediction that our model outputted for each of the words, and you can use the corresponding indices to find out which tag was predicted based on the indices we defined for all of the tags earlier. I hope you guys have learned a lot from this course. Do leave your feedback on the contact details we will provide at the end in the description box. Thanks a lot for watching.